anything that occupies space and has a mass. Matter is complex. It can be organized in many different levels. On my way. You're living, you occupy space, you have a mass, you matter. Aww. Aww. So, our three states of matter that we can review for now are solid, liquid, and gas, right? So, we learned in Chemistry 1 that a solid has a definite volume and a definite shape. Liquids have a definite volume but an indefinite shape, and gases have both indefinite volume and shape, right? Something hopefully remember, or just, common knowledge, might know that. This is a little flow chart to help you determine if matter is a pure substance or if it is a mixture, okay? So remember our different types of mixtures. We have homogeneous and heterogeneous. Which one of those is when you can tell there's a difference? Heterogeneous is when you can tell there's a difference. Like if you have raisin bread, you can see the raisins in the slice of bread. Okay? And for pure substances, those could be elements or compounds. And elements can be broken down further into metals versus nonmetals, because we have that grouped on the periodic table. And metals could also be broken down into magnetic versus non-magnetic metals. So this flowchart is just a helpful way for you to try and organize identifying things. We will do a lab this year that you will be given some unknown material, and you will have to determine what type of compound it is based on results from a flowchart that you design. So getting to know flowcharts is a good idea. Okay, so to review from Chemistry 1, a physical change is a change in the form of a substance, not its chemical composition. Physical changes can be used to separate mixtures into pure compounds, but it will not break compounds into elements. So physically, the identity of the substance will remain the same. So does anybody have an example of a physical change? Freezing, melting, boiling, all of those phase changes, states of matter changes, are all physical changes. Because if you have an ice cube and it melts, when it's frozen, it's made out of water. When it's melted, it's made out of water. So it's the same identity. So that would be the hint that it would be a physical change. Okay? Like I said, boiling, freezing are examples. Okay. One way to perform a physical change is to separate mixtures. Well, we have a couple different ways of separating things. Some we did in Chem 1 and some you have not done before, but we will do this year too. One of the ways is distillation. So I don't do it in this setup, but this is how we make distilled water in this class. With my machine I have in the back, what it does is you will heat up water that we get out of the faucet until it turns into vapor. And then the vapor will travel through a condenser, which will cool it back down, turning it back from a gas phase into a liquid phase, and we can collect the liquid, distilled, pure liquid. If you ever look in the actual thing that I have that makes it, after it's done, all of like the lime scale that's left over from our well water is pretty gross. So anytime you want to see that, I can show you. But all the gunk is left over back in your original flask or vessel when you're done, because that's all the stuff that you get out of the water. Now, do I think my machine is perfect and makes the best distilled water you could ever have? No, because the pH is not actually the right pH value, but it's a lot better than what we had before. Filtration is another way to separate, where you usually will use filtration if you have a solid mixed in a liquid. So we use funnels and use filter paper to collect just the solid residue and have the liquid come out. It's called filtrate. When we do this, we did this in Chem 1, right? At one point, we had to let the paper dry overnight and then weigh it again. And if you had a greenish tint to it, you didn't actually wash it properly. And so not only do you let the filtrate go through, the liquid go through, but you also have to wash it with water to make sure that it's just the pure solid you want and there's no residue from the liquid left on it. And last but not least is chromatography. We haven't done this before. You might have done this in a different science class or something. Has anybody ever done chromatography before? Or if you're on Science Olympiad forensics team, you do this every year, where you separate like an ink or a dye. We're going to use food dyes, like you've ever heard of red dye 40? We'll have a mixture of food dyes that you will separate in a chromatography lab. And the first one we do, and I'll tell you, these are the colors that you should have in it. And then the second round, you will pick your own mixture that I've made for you, and you separate it, and you have to see how many colors are in that mixture. So it's just a way to show, usually they're mostly liquids. You can also do this with like markers, pens, ink pens, anything like that also works, but we use food dye because I have it. So chromatography is another separation thing. Okay, so if we're not physically changing things, then we are going to chemically change things. Chemical change is when the substance becomes new and different substances. So it has different properties and different compositions. An element is a substance that can't be decomposed into anything simpler. Just a note that when you have a chemical change, you're technically also having a physical change, but so when it's chemical, you also have physical, but when you have physical, it's not chemical as well. So sometimes people have a hard time with that, because usually, like, if you're flaming up your marshmallow over the bonfire, it's going to look different at the end than at the beginning, right? So physically, it does change as well as chemically, okay? Hopefully, that's pretty much a review from Chem 1, right? Okay, so now getting into our percentages that we had yesterday. You know, when we did the empirical formula and molecular formula, and in our example, I said, oh, we have 71.65% chlorine, okay? Where does that percentage come from? That is called percent composition, okay? So there's two common ways of describing the composition of a compound: by the numbers of its atoms or by the percentages by mass of its elements. So the mass percents are those percentages that you were given yesterday, okay? But we can solve for those percents using molar mass, using experiment data, anything like that. So you can find them from comparing the mass of each element present in 1 mole of the compound to the total mass of 1 mole of the compound. The mass percent can be computed multiplying by 100 after you divide the part divided by total. Do I have an equation for you? No. So if you needed an equation, the mass percent would equal the mass of the part, which could be an element, over the mass of the total compound. Times 100. So hopefully we kind of have an understanding of how percents work, right? Where, like, if your grade's a 95%, that means you, out of 100 points, you get 95 correct. Okay? So the part would be whatever, usually the smaller number will go in the top. Hopefully you know that. Okay, so in this example, we are not given any numbers, so we are going to use molar mass to solve. If you were given experimental data, you would use that data, but in this case, we just have nothing, so we'll use molar mass. Okay? So carbone is a substance that occurs in two forms, having different arrangements of the atoms, but the same molecular formula, which is C10H14O, and mass. One type of carbone gives caraway seeds their characteristic smell. Do you guys know what caraway seeds are? They're found in, like, rye bread, the seeds in rye bread. Maybe? Okay. And the other type of carbone is responsible for the smell of spearmint oil. That's two completely different things because when you have rye bread, it's not really minty, is it? So it just depends on the way that their chemical structure is arranged. So we want to compute the mass percent of each element in carbone. Sometimes I might say, what's the mass percent of just carbon? So you would only have to do one. But if you are not given just one element, then you will solve for all the elements involved. So how many answers will we have? 3. Because we have carbon, we have hydrogen, and we have oxygen. Okay? So, space for me. So, we're going to keep them separate when we solve. Okay? The first thing that we need to do is we need to make sure we include all of the mass of each element in the numerator when we're dividing to find the percentage. Okay? So, the structure was C10H14O. So when we do carbon and when we do hydrogen, we need to make sure that we multiply the molar mass of those elements by the number of atoms involved. Okay? So we will take 10 times the molar mass of carbon, which is, I think on your new periodic table, is 12.01. If you would like to get more accurate, you can, if you wanted to. And then hydrogen, we will take 14 times 1.01, I think it's on your new periodic table, to find the total mass of hydrogen involved there. And what's going to go in the bottom of these? The entire molar mass of the whole thing, right? So let's just go ahead and do that, because remember, we did this in chemistry 1. If you know 2 of them, you can subtract from 100 to find a third, because all of the percentages should add up to 100, so that would potentially be easier to solve for that way. Okay, so does anybody find the total molar mass? Yeah? 150.24. Okay, so if you need to make note of this in your notes, the total molar mass for the compound is 150.24. Okay, so that 150.24 will go in the denominator every time you divide. Okay, and then each one we need to make sure we multiply by 100 to solve. Do you guys want to just subtract from 100 for oxygen, or would you rather practice the setting up to find the percent? Subtract? Okay. All right. Since we don't have any numbers in this problem, let's just go to 2 decimal places. So, because we don't know what to round to sig figs for, so let's just go to 2 decimals. Anybody get one of them? 79.94%. And the unit is percent. Okay. Anybody do hydrogen? 9.41%. Okay. So then if you wanted to, you could take 1 times 15.999 divided by 150.24 times 100. Or we can just take 100 minus the 79.94 plus the 9.41. Usually I do that because it's simpler for me. And that one is 10.65% oxygen. So all 3 of these numbers are answers, since I didn't specify which element to solve. Okay, so you can do this with any compound, any formula you're given. But this is just like the opposite way of what we did yesterday, where you can be given a formula and solve for the percent by mass, or you can be given the percentages and solve for the formula. They kind of go hand in hand either direction. Okay? So that's it.